All right, let's get into it. Propellers. They're everywhere, right? Powering everything from tiny little drones to absolutely massive container ships. But have you ever really stopped to think about them? I mean, it looks so simple, just a few blades spinning around. But behind that simple motion, there's some seriously cool and surprising science going on.
So that's really the big question we're tackling today. How on earth does this spinning, fan-like thing generate enough force, what we call thrust, to push a multi-ton airplane through the sky or a giant ship through the water? Well, the answer starts with a fundamental law of physics from way back in the 18th century.
And there it is, good old Sir Isaac Newton's third law of motion. You've heard it a million times, but this is the key to all propulsion. I mean, everything. Whether you're walking, swimming, or flying a supersonic jet, the basic principle is exactly the same.
To boil it all down, it's this simple. If you want to go forward, you have to push something backward. And in this case, that something is a fluid, like air or water. A propeller is basically just a super efficient machine designed to do nothing but push that fluid backward. So the real question becomes, what's the best way to do that?
Well, the first and maybe the easiest way to wrap your head around a propeller is to look at something you've definitely got lying around in your garage or a toolbox somewhere.
That's right, a screw. In fact, the early inventors literally called them air screws or screw propellers. And you know what? The analogy is actually incredibly accurate and powerful. Think about how it works. It's a simple but brilliant little machine. You apply a turning motion, that's torque, and that spiral thread on the screw magically converts that rotation into a really powerful linear motion, pulling it straight into a piece of wood. And a propeller does the exact same thing. The engine provides that turning force, and the blades are shaped to bite into the air or the water, pulling the whole aircraft or ship forward. But this brilliant analogy has a twist, literally. Because while thinking of it as a screw is a fantastic starting point, it isn't the whole story. Not by a long shot. To really truly understand a propeller, you have to stop thinking of it as a screw and start thinking of it as a wing. And this was the stroke of genius from the Wright brothers. They were the ones who realized that a propeller blade wasn't just some crude paddle pushing air. No, it was an actual aerodynamic surface, working on the exact same principles as the wings on their plane. So get this, instead of generating lift to fight gravity, our propeller's wing is just turned sideways to generate thrust, pushing the aircraft forward. It's all the same physics, pressure differences, airflow, all of it, just pointed in a different direction. And you can see here, each blade has all the same parts as a wing. You've got that classic airfoil shape with a rounded leading edge and a sharp trailing edge. The root is the part that connects to the central hub, and the tip, way out here, is the fastest moving part of the whole thing.
Okay, but this brings up the most important question. If you ever look closely at a propeller blade, you'll see it's not flat. It's twisted along its entire length. And that is not an accident. It is an absolutely critical piece of engineering.
And here's why. Think about a spinning vinyl record. A point on the outside edge has to travel a much greater distance in one rotation than a point near the center, right? Well, the exact same thing is true for a propeller. The tip is moving at an incredibly high speed while the root is moving way slower.
So to generate a smooth, uniform amount of thrust all along the blade, you have to account for that massive speed difference. The twist gives the slow-moving root a steeper angle so it can take a bigger bite of the air, while the super fast-moving tip gets a much shallower angle. Without that twist, the forces would be all out of whack, and the propeller would be terribly inefficient and probably shake itself to pieces.
Okay, now things get even cooler. What if you could actually change that twist, or what pilots call pitch, while you're flying? That brings us to the next level of propeller sophistication.
So, you've basically got two main types. On one hand, you have a fixed pitch prop. Its angle is set, and that's it. It's simple, light, cheap, but it's a compromise. It's like being stuck in second gear forever. Then you have the variable-pitch propeller, which can change its blade angle on the fly for maximum efficiency, no matter if you're taking off, climbing, or just cruising along. And honestly, this is the absolute best way to understand it. Having a variable pitch propeller is almost exactly like giving an airplane a manual transmission. For takeoff, you want what's called a fine or low angle pitch. The blades take smaller bites of air, which lets the engine spin up really fast to generate maximum power. That's your first gear. Then, once you're up at cruising altitude and speed, you switch to a coarse or high angle pitch. Now the blades are taking huge bites of air, moving the plane a lot further with each rotation. That's your fifth gear for efficient highway driving.
Okay,
So far, we've pretty much been talking about air screws. But what happens when your propeller needs to work in a fluid that is much, much different than air? And here it is. This is the single most important number you need to know when comparing a plane propeller to a ship propeller. Seawater is nearly 1,000 times denser than air. 1,000.
That one fact completely changes the rulebook. It dictates almost every single design choice. You just can't use the same tool for two wildly different jobs. Pushing against something as thick and heavy as water requires a totally different strategy than pushing against thin air. And the design differences are just night and day. Aircraft propellers are long, they're thin, they're made of lightweight materials, and they spin incredibly fast. Ship propellers, on the other hand, are short, broad, super heavy, and they spin much more slowly to efficiently move all that dense water without just churning it and wasting energy.
Ship propellers also have to deal with this really nasty problem called cavitation. If they spin too fast, the pressure on the blade drops so low that the water around it literally boils, creating these little bubbles of water vapor. And when those bubbles collapse, they act like thousands of tiny explosions that can blast chunks of metal right off the propeller and destroy it over time. The amazing thing is, the innovation just never stops. I mean, we've gone from the Wright brothers hand-carving blades out of wood to modern computer-designed composites, and even these radical new ships like toroidal propellers that look like weird rings. We are always finding new ways to make this seemingly simple machine quieter and more efficient. It really makes you wonder, what's the next big leap forward in propulsion going to look like?